Hello everyone. Today I am Rishabh Bhardwaj, Assistant Professor in St. Andrews Institute of Technology and Management, taking the lecture of heat transfer. In this lecture, we will study about unsteady state or transient condition in sphere. Now, let's start with the uh, transient conduction. Initially, we have to consider a solid body which is having a mass m and the volume v with the density rho and the specific heat capacity that will be the Cp, which is at the which is at an initial temperature of Ti. That I denotes the initial and having the heated in the furnace, and it's suddenly exposed to an ambient fluid which is at temperature of T infinity. Here m denotes the mass, v denotes the volume, and rho represents the density, and Cp represents the specific heat of the system. We have taken a solid body and that ambient temperature, that will be the T infinity, and the A is the contact area. Since the body keeps on losing heat by convection to the ambient fluid, that is a thermal reservoir, with a conductive heat transfer coefficient of H, the internal energy of the body keeps on decreasing as the time progresses, which is manifested by the decreasing of temperature of the body with respect to time. Let's take the Ti is equal to initial temperature of body at the instant of time, where tau is the second, that is when body is exposed to ambient fluid. The T is equal to the temperature of the body at any instant of time tau second. Later, writing the energy equation for the body at any instant of the time tau second, the rate of convection of heat transfer between the body and fluid, that will be the rate of decrease of internal energy of the body with respect to the time. That equation that will be formed, that is HA and change of temperature, where H is the coefficient of convection and A is the area, and T stands for the internal temperature, and the T infinity is the temperature of the ambient fluid. That will be equal to the minus with the minus sign of mCp dt by d tau in the joule per second. If we simply write as that HA T minus T infinity is equal to minus rho v Cp dt by T rho, where m is replaced by the term m, as we know that rho is equal to mass by volume, the density is mass by volume. By the help of this, we replace the value rho v by m, treating all other parameter including h as constant and separating the variable time and temperature. We will get the equation, that is integral with limit 0 to tau HA by rho v Cp into d tau is equal to the negative sign of dt by t minus infinity integral with the limit ti to t. where if we integrate the value of d tau and taking the HA and HA by rho VCP as a constant and putting the value of tau limit, that will be 0 to tau, and d tau will be integrated as tau, and in the second on the right hand side the value will be turned into minus natural log t minus t infinity, where limit will goes to minus t initial to the final t. If we putting the values and write the equation like h a into tau by rho v cp is equal to minus natural log t minus t infinity plus log t initial minus t infinity. If we taking the dividend rule across the natural log, we can write the equation as natural log the bracket of t minus t infinity by ti minus t infinity. That will equal to minus h a tau rho v cp, where h a by rho v cp is in second per second square and rho v cp by ha has got the unit of second. By replacing the value and multiplying both sides with the exponential term, then from the left hand side the natural log will get diminished and the value that remains, that will be t minus t infinity upon ti minus t infinity. That will equal to the exponential's power minus h a tau by rho v cp. Hence, in any unsteady heat transfer, the temperature of the body changes exponentially with respect to time. As you can see in this figure, the graph shows that the values are decreasing, or the value initially is so high and the value will get smaller as with respect to time. During the unsteady state, the heat transfer, the rate of cooling or heating of body itself become a function of the initially the rate of cooling is very high. Due to high convection heat transfer rate between body and fluid, because of large temperature difference between them. But as the time progresses, this rate of cooling decreases due to reducing heat transfer rate between body and fluid because of lesser temperature difference between them. If we take the heating case, that will be the dt by d tau. That will be the that will be greater than 0. That is a heating rate. In that case, when a body is picking up heating or get heated, the rate of heating also decreases as the temperature varies. But with the passage of time, the rate of heating will get changed. For the time constant, the HA by rho VCP, that will be the per second, and has got a unit of second. This group is called as time constant. This time constant of body signifies how much time will be taken by the body in approaching the difference of the thermal ambient when the body suddenly exposed to it. For this we have a it will become a thermocouple, in which
of gases around the sphere body, and the time constant that will be taken as smaller as compared to as smaller or congruent to the 2 seconds. Here we become the thermocouple. The time constant of thermocouple is very small because coefficient of convection value is very high. Here V by A is equal to the volume of sphere, that is 4 by 3 pi r cube, upon the area of sphere, that is 4 pi r square. The size of the bead is very small and the heat capacity, that is rho Cp, is also small. Then thermometer time constant is equal to the 90 second. In the above analysis done, it is assumed that the temperature of the body is uniform throughout its mass at any instant of time. That is, internal temperature gradient within the body are neglected. The if we have a sphere and internal core area, and this is the periphery, the change of temperature at any instant of time, that will be the zero, and such that there is temperature is time function but not the location and the space. Such analysis, it's called lumped heat capacity analysis. Let's discuss the criteria for lumped heat capacity analysis. For this, the Biot number should be less than 0.1, where Biot number is the Hs by K solid, where S represents the volume of body upon surface area of the body. Then the Biot number will become internal conductive resistance offered by body upon external convecting resistance. The low Biot number value signifies that the body offers very little conduction resistance for any internal heat transfer within the body as compared to the surface convective resistance, thereby leveling the temperature difference thereby leveling the temperature differences that may exist between any two locations within the body. For that example, that any metallic body reasonably small size having a very rapid conduction and slow convection. You can note it down as if a body is very small, then it will gain or it will conduct heat energy as early as possible. But as compared to the convection process will taken be very small or very slow. Okay, next we have relaxation method. The relaxation method is a numerical method of solving a set of algebraic equation that was first used by the Sir Richard Southwell. The basic principle of the relaxation method is to show the algebraic equation. Like for the example, we have two equations, that is minus 15x plus 16y is equal to minus 279, and the second condition we have 5x minus 24y equal to minus 145. To obtain the solution from this equation, we have put these values to one side and put it the values as R1 and R2. In this case, we have
proven that the R1 will be the minus 15x plus 16y plus 279. In the R2 that will be equal to 5x minus 24y plus 145, where R1 and R2 known as the residuals. The objective of the relaxation method is to reduce the residual systematically to 0 or close to 0. The value of x and y which makes the residual 0 are desirable values. Since they satisfy the given equation, the first step in the solution is to choose the initial value of x and y. For that we have supposed the value of x and y that will be the 0, and for that the residuals become R1 is equal to 279 and R2 become 145. In the second step, is to set up an operation table which will indicate the effect of unit positive increment in the value of x1 and x and y on the residuals. The operation table of the present problem could be shown as mentioned below, that the increment value that will be the x changes the value of 1 and the y simultaneously 1, then the change of R1 and R2. The third step is to reduce the currently large residuals to 0, since the largest residual R1 is 279 and change of x could be 19 and R1 will be minus 6 and for R2 will become 240. The second and subsequent step concentrate on the currently largest residual to find the incremental changes in x and y to reduce the residuals to 0 or close as possible to the 0. The subsequent calculations are summarized in tabular forms. The last row in the table given the values of x and y which are correctly to the nearest whole number. Then the calculation can be redefined to obtain a solution for the first decimal place by using the first decimal increment. Further refinement can be made in a similar manner depending on the required accuracy of the final solution. A summary of first decimal and subsequent increment calculation can be formed in the like this. In the you can see in this table that the first increment value that could be taken, that is 0 0. For that the R1 and R2 become 279 and 145. If we change the value into x, change of x is equal to 19, then value of y become the difference, the value of will become the difference of between them. It means the change of value into x by into 19, we have to minus out the two values in them, by which 279 minus 6 and become the 154 and 145, that value becomes the 240. Then the value of will be change of y is equal to 10, then the value of R1 will be 154 and R2 will be 0. The change of x with respect to 11, then the value become minus 11 and R2 value will be 55. The change of y, that value will become 37 and R2 value will be minus 17. For the change of x is equal to 3, then the value become R1 is minus 8 and R2 is minus 2. That implies that the x will changes to 33 times, or the number 33, and y is equal to 13. The value of minus 8 and 2 will be gained from the system. In the similar way, in the table 2 you can see that 33, then we change the values in the decimal forms, and if we take the values x is equal to minus 0.5 and minus 0.2, then in case the minus 0.5 value of R1 and minus 0.5 value of 4.5 will come into the right R2, and for the change of Y for minus 0.2, the value become minus 3.7 and R2 will become the 0.3, and change of X is equal to minus 0.2, then the value of R1 will become that minus 0.7 and R2 will be the 0.7. It means the row marked A and the solution which are correct up to the first decimal place, the row P will be the table above the residual are zeros. Hence it gives the final values of X and Y to 32.2 and the 72.75 respectively. If we're talking about the shortcut method in this relaxation, the relaxation method can be also be applied by the complex problems. However, by the modification of the method can be save considerable effort and the time. These modification can be called as the shortcuts. For the shortcut method, we have to follow up the some steps that are the first shortcut is to assign some initial values to the variable. Instead of assigning the zero values, the initial value can be guessed or based on the close look at the physical problems. And the second shortcut called with our over relaxation is used to change the residuals from the positive value to the negative values, or could be the vice versa. By choosing the largest increment, however, one of the cannot be quantified the size of the increment to choose. The choice of the increment may vary from the person to person or analyzing the problem. The third shortcut can be called as the block operation, and that is to be changed the each of the variable by the same amount and the change of the residual due to the individual unit increment in the variable at in the stage of the calculation, but it is quite variable in the initial step of the calculation to apply this unit block. Or the unit block operation, in the initial step we add the residual and divide this sum of the effects of the obtained in a block operation. It will be the size of the increment if one uses the increment size thus obtained in a block operation. It will reduce the sum of residual to 0 and the initial step considerable, reducing the subsequent step to obtain the final solution. Now, what are the application of the relaxation method? If we discuss that in the numerical method of the analysis of heat transfer problems, and the differential equation and the boundary condition are expressed at the set of the algebraic equations. The algebraic equation can be solved by the relaxation technique, and over the relaxation and the block unit operation are the most powerful and the shortcut way by which we can introduce the relaxation to save the considerable effect and the time in the analysis. This is come to an end, and we'll stay tuned for the next video. Today we have just discussed the relaxation method and the transient conduction in the sphere, by which we are able to know how much quantity and the how it has been transferring the heat energy from a sphere, and how the relaxation method will allow us to change and give the values of the algebraic equations. Thank you for watching this video and stay tuned for the next one. Thank you.